Have you ever imagined an invisible shield protecting an entire continent? That's the idea behind the Golden Dome, a massive space-based missile defense system proposed by the United States. In the next 10 minutes, we're going to break down this multi-trillion-dollar concept. We'll explore why cost estimates are all over the map, from an initial $175 billion to potentially trillions. We'll look at the mind-blowing technology it requires, from AI-driven battle management to swarms of orbiting interceptors. Finally, we'll examine whether this sci-fi shield is a genius strategic move or an impossibly expensive fantasy. Stick around to understand the future of warfare. The Golden Dome is one of the most ambitious defense projects ever conceived. It's a proposal for a multi-layered, space-enabled missile defense architecture. Think of it as a celestial net of sensors and interceptors designed to shoot down incoming threats before they can ever reach North America. Officially announced in 2025, the White House pitched an initial program cost of $175 billion to get things started. But that's just the down payment. Independent analysts and government budget offices are looking at the full life cycle, and their numbers are staggering, ranging from hundreds of billions to potentially trillions of dollars. So why the huge difference in cost estimates? It's because Golden Dome isn't a single thing. It's a system of systems. It combines space-based sensors, interceptors on orbit, advanced command and control software, and it has to integrate perfectly with existing ground and sea-based defenses. Even small changes in the design have massive financial consequences. For example, how many interceptors do you put in space? Are they single-use, or can they be reloaded? What altitude do they orbit at? The lower the orbit, the faster they fall back to Earth, meaning you have to replace them constantly. Each of these decisions can add or subtract billions, which is why a politician's initial sales pitch of $175 billion looks so different from a decades-long projection that might exceed $1 trillion. Let's look at the credible cost bands being discussed right now. First, you have the political number, around $175 billion. This is the figure the administration is using to kickstart the program, covering initial research, development, and a first batch of hardware. It's designed to sound achievable. Then you have the independent analysts, like the Congressional Budget Office. They factor in everything: long-term operations, maintenance, and the constant need to replace satellites. Their estimates for just the space-based components often run between $160 billion and over $500 billion over 20 years. Finally, some think tank analyses model a truly robust system with thousands of interceptors and a continuous launch schedule to replace them. In these scenarios, the total cost over several decades could easily push past $1 trillion. These high-end estimates depend heavily on how many interceptors we lose over time and how much it costs to replace them. So where does all that money actually go? The biggest cost driver is the hardware in space, the satellites and interceptors themselves. Even a modest cost increase per satellite gets multiplied across a constellation of hundreds or thousands. Next is the cost of launch. Putting all that hardware into orbit requires frequent rocket launches, and that adds up to billions very quickly. Then there's the brain of the system, the software. Developing the advanced AI and sensor fusion capabilities is a massive engineering challenge in itself. And don't forget sustainment. Satellites in low Earth orbit don't stay up there forever. They have to be refueled, repaired, or replaced, creating a constant, recurring bill. The one-time research cost is just the beginning. The real expense is in building the system and keeping it running for decades. To make the Golden Dome a reality, we'd need major technological leaps in at least 5 key areas. First, we need affordable, mass-produced space interceptors. The cost per kill vehicle has to drop dramatically to make a large constellation viable. Second, we need advanced persistent sensors. This means new types of infrared, optical and radar sensors in space that can track fast-moving hypersonic missiles from launch to impact, all networked together for a complete picture. Third is rapid low-cost launch. We need to be able to replace and resupply the constellation cheaply and on demand, which makes reusable rockets absolutely critical. Fourth, we need AI-driven command and control. Sophisticated algorithms are required to process all the sensor data, assign the right interceptor to the right target, and do it all in seconds. In this system, the software is just as important as the hardware. Finally, the whole system has to be resilient. It needs to defend itself from anti-satellite weapons and cyber attacks, which means new materials, new defensive tactics, and distributed networks that can't be taken down by a single point of failure. If these technological hurdles can be cleared, what are the potential game-changing advantages? The biggest operational benefit would be the ability to detect and engage threats much earlier in their flight path, especially during the boost phase right after launch. This is the holy grail of missile defense. A space-based layer also creates a distributed defense. Instead of relying on a few ground-based sites that an enemy could overwhelm, you have hundreds of interceptors in orbit, making it much harder to saturate the system. Ultimately, it would create a tightly integrated sensor-to-shooter loop, dramatically cutting down the time from detecting a threat to destroying it. In theory, moving missile defense to space provides earlier warnings and protects a much larger area. But that's a big if, dependent on solving some very hard problems. And those problems are indeed very hard. Space is an unforgiving environment. Objects in low Earth orbit are constantly being pulled down by gravity, meaning interceptors there would have a short lifespan and need constant replacement, which is a huge recurring cost. Intercepting a hypersonic missile that's S-maneuvering at 5 times the speed of sound requires incredibly precise guidance. And while futuristic options like space lasers are often mentioned, they face immense challenges with power, aiming, and heat dissipation. Beyond the physics, there are practical issues. How do you test a system like this realistically? And what about enemy countermeasures? An adversary isn't just going to sit back. They'll develop decoys, electronic jamming, cyber attacks, and anti-satellite weapons to defeat the shield. These are the reasons many experts remain skeptical, questioning if a truly impenetrable space shield is either affordable or even possible against a determined, technologically advanced opponent. So, what's the timeline for all this? The program was announced with very aggressive goals, including having some initial capability within just a few years. Right now, government program offices are being set up and defense contractors are lining up to compete for a piece of the pie. But we should expect an iterative process. We'll likely see small-scale demonstrations first, followed by gradual increases in capability as technology is proven and funding is approved. The political timeline of getting something working within a single presidential term is extremely optimistic. A realistic deployment of a fully operational Golden Dome architecture would likely stretch over a decade or more, paced by budgets, test results, and the complex geopolitical landscape. Speaking of geopolitics, deploying weapons in space is a hugely controversial move. It would undoubtedly trigger a strong diplomatic backlash, especially from countries like China and Russia, who have already criticized the concept and would view it as a threat to their own deterrence. This could spark a new arms race in space. These geopolitical pressures could force design changes. For example, relying more on ground-based systems or partnering with allies for hosting sensors. Any of these changes would impact the final cost and effectiveness. Furthermore, an adversary might respond not by building their own shield, but by developing cheaper asymmetric ways to counter it, like anti-satellite weapons. All of these strategic and legal implications add significant risk and cost to the program. However, a massive project like Golden Dome would also have significant side effects on the commercial space industry. The huge defense investment would accelerate development in low-cost launch, satellite manufacturing, and AI analytics. This could create economies of scale, driving down costs for everyone and spinning off new technologies for the commercial market. But it's a double-edged sword. While commercial companies would benefit, the primary beneficiaries would be the major defense contractors, and taxpayers would be left with the long-term bill for maintaining the system. The true value depends on how much of this investment creates genuinely new, do-or-lose commercial opportunities versus just becoming a massive defense expenditure. So, what's the bottom line? How should we judge the Golden Dome as it moves from concept to reality? The key things to watch are the official cost analysis from budget offices, the results from early technology demonstrator tests, and the real-world economics of launch and satellite servicing contracts. Success won't be measured by grand political announcements, but by testable, repeatable performance at a cost that the country can actually sustain. If the technology works and industry can innovate to bring costs down, the system could provide a powerful strategic advantage. But if it becomes a fiscal black hole, it could weaken the nation by diverting resources from other critical needs. The dream of an invulnerable shield is alluring, but the reality will be determined by cold, hard physics and economics. Thank you so much for joining me on this deep dive into the Golden Dome. It's a fascinating, complex, and incredibly important topic that will shape global security for decades to come. If you found this video informative, please hit that like button and subscribe to the channel for more content just like this. We love hearing from you, so leave your thoughts and questions in the comments below. Thanks again for watching, and we'll see you in the next video.